Alright, today we're going to have our last lecture in Unit 2, and we're going to focus on the binomial and hypergeometric distributions today, along with a part involving tables for the normal distribution near the end. Binomial and hypergeometric are usually the parts that students find to be the most difficult about this unit. So we're going to go through great length to explain where they come from, the differences between the two, and associated shortcuts. So when it comes to the binomial distribution, it's useful to first understand the concepts behind it. So when we have binomial trials, they're often referred to as Bernoulli trials. And a Bernoulli trial is one where you have a success or a failure. That's it. Those are your only two options. Now, sometimes a success might very well, as a practical matter, be a failure. So when we say success and failure, we put air quotes around that. For example, if we're looking for a failing student, then we might succeed at finding the failing student. So it's very much so a terminological kind of thing. For those of you that are familiar with computer science, it might be easier to think of it as true-false, where true is success and false is failure. We can have a certain number of these trials. However, in every single trial, it needs to be identical. That is, it needs to be success-fails or true-false, and the probability of success needs to be the same every single time. This ensures that they are independent of each other, and that a success or a fail on a previous trial does not impact whether or not the next one is a success or a failure. Thinking that a success or failure means you're more likely to have a success or a failure on the next trial is actually known as the gambler's fallacy. You see a bunch of idiots in Vegas doing this all the time. This is why casinos make money, at least in part. So here, we'll recall the tree diagram from Unit 1. So here, let's suppose we have 3 trials where we have customers and we're trying to sell them a car. You can have up to 3 sales of a car, or you can fail every single time. Now here, the order does matter. Now you might say to the dealer, oh, well, I sold 2 cars, doesn't matter who I sold them to. Absolutely does matter who you sell them to. Go out, walk up to any dealer, and they'll tell you that. So the order does matter. So, although there's only one way to get 3 successes, so succeed, 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 which is our top one, and there's only one way to get 3 failures, i.e. you screw up every single time, there's multiple ways to get ones in between. There's 3 ways to get 2 cars sold. You can succeed the first time, fail the second, and succeed the third. Alternatively, you can succeed the first time, succeed the second, but fail the third. On the other hand, you can fail the first time and succeed the remaining 2 times. So therefore, we have 3 ways to sell 2 cars each. Similar logic holds for just 1 car. This tree diagram composes all the possibilities for 3 Bernoulli trials. And we have what we call X. In this case, X is the number of successes. So, previously, our inputs dealt with one particular trial. Now, we'll typically do these over multiple trials and ask us how many times do we succeed. Or you can define as how many times you fail, but same idea. So this is important for defining the binomial distribution. So the binomial distribution we denote by b of x, b for binomial, and this is where the factorials come into play. So here we have n factorial, and our denominator is x factorial times the quantity n minus x factorial. In this case, n is the number of trials. X is the number of things that are successes. And again, success might sound a bit weird depending on the context. if we have 25 of you and 3 of you fail the Unit 2 test, and I ask, what are the chances I pick 4 students and 2 of them fail, then the success would be picking somebody who failed. So it can seem a little bit weird at times. That's why sometimes thinking it as true-false can help. And then P is the chances of a success happening. So here, the next part, we multiply this quantity, this fraction, by our P to the power of X, where X is our input. And then we have the quantity 1 minus P. We raise that to the power of N minus X. For any given problem, you will have N and P straight out of the gate. So when you're setting this up, you'll already know this, and you'll put that in. So say it could be 5, so 5 factorial. You'll already have this. You'll already have this. You'll already have this, and you'll already have this. So like with the Poisson distribution, the only thing you're going to be inputting after you've set it up is your value of X. Now, with regards to entering this into Desmos, again, I strongly recommend that you go over the Desmos Assistance video to teach you how to input this. Unlike with the Poisson distribution, it's far easier to have a typo. If you have a typo, the whole thing's going to be wrong, and you're going to get negative probabilities or probabilities over 1, and it's not going to make any sense. Now, for the binomial distribution, the mean or expected value of the binomial distribution is equal to the number of trials times the probability of success, and that intuitively makes sense. If you are, say, doing it 10 times and there's a 50-50 chance of success, then 5 of them should be successes, 5 should be fails on average. And the variance is equal to the mean times 1 minus the chances of it occurring. So, the lower the chances of it occurring, the more variance that you could have. And depending on how you define a success, the reverse can be true as well. But as we saw with before, the closer we get to 50-50, the more variance we have. And in fact, when we get to units 3 and 4, we'll algebraically show why that's the case. So you might say, okay, this is all fine. When do I use this? This is not a pretty formula, and I see we have 4 conditions. This looks much more complicated than the previous 2, because oftentimes it is. So in order for something to be a binomial distribution, it must satisfy the following 4 conditions. 3 of these are, in fact, Bernoulli conditions. So we have n identical trials, the probability of success doesn't change, and only 2 outcomes per trial. Those are all Bernoulli conditions. You might say, what? I thought there were only 2 Bernoulli conditions. Well, now with the binomial, it's multiple trials, so we put them together. Essentially, condition 3 is just doing multiple Bernoullis. So these first 3 just are confirming that it's a success-fail trial. Condition number 4 is what differentiates the binomial distribution from the hypergeometric distribution. Condition number 4 states that the trials are independent, i.e., a success on one trial does not impact a success on another trial. There's a much easier way to summarize all of this. So to summarize, the binomial distribution, where is my colon? There we go. So to summarize, the binomial distribution is used for replacement. You might say, replacement where? Where'd this come from? Think of it this way. Imagine if we're flipping a coin over and over again. Obviously, it's the same trial every single time. We just keep flipping the same coin, so condition 1 is satisfied. Condition number 2, there's only 2 outcomes. It's heads or tails. You might say, ha! I bet you I can make it lay on its side. Have fun with that. Have fun genuinely flipping a coin and getting it to land on its side. Technically, physically possible. As a practical matter, doesn't make any sense. And of course, it's 50-50 every single time, so the probability doesn't change. The fourth part, and this is the key part, it's 50-50 odds every single time. Whether or not we get heads or tails on one trial does not impact the other one. What this means, think of it this way. All of these can be summarized as we're replacing the coin with itself every single time. We flip the coin, we take the coin back, we flip it again. Just because the coin landed on heads, we don't put a weight on the heads to increase the chances of tails occurring. We keep flipping the same coin over and over and over and over again. Here's another example. Imagine you have a deck of cards, 52 of them. You pick a card, you see what it is, you put it back in. And I ask you, what are the chances of getting a queen? Well, you pick the card, 1 out of 13, because 4 queens in a deck of 52, 4 out of 52 is just 1 out of 13. You pick it, you put it back in, and you do it again. By definition, you literally replaced the queen by putting her back in. So binomial is for replacement. So here, it can help to have a few examples. So here, example number 5, we're going to construct you can do a tree diagram, you can do a table like with discrete probabilities. What I want you to do is do examples 5 and 6. Both of these are binomial. What I want you, it doesn't ask you to do, but you should ask yourself what makes it binomial. See if you can figure out where the replacement part is. And then I want you to do both of these, and we'll go over the answers. So let's start with this one. Toss a coin 3 times. Well, we're going to make our table. So we have our outcome and then the probability. So I made that a bit too big. Here, we're going to use b of xi to denote binomial. So we're saying a head is a success. We do it 3 times. So we can have 3 heads, 2 heads, 1 head, or no heads. What are the chances of getting 3 heads? Because it's replacement, it's going to be 1/2 times 1/2 times 1/2. This is equal to 1/8. So therefore, the chances of getting all heads is 0.125. In a similar vein, if we have tails, that's going to be 1 minus 1/2, complement law, times that, so to the power of 3. That's also 1/8, so 0.125. With 2 and 1, there's 3 ways we can have each of them. It could be heads, tails, well, let's say with 1, heads, tails, 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 heads, tails, or tails, tails, heads. So regardless, 3 ways. The other way you can think of it is these 2 have to add up to 75%, and they both have equal chances of occurring. So it would follow that it has to be 0.375. Now, I want to point out that for 3 and 0, we actually just found shortcuts. So I'm going to introduce you to those. These are the binomial shortcuts. You get to use the binomial shortcuts when we are looking for always success or never success. And here's why this is the case. So what I'm going to do is I'm going to copy paste this formula and show how this formula simplifies down to these 2. So let's start with our first one. If we always succeed, n factorial, we don't know what it is, doesn't matter. If we always succeed, then x is equal to n, because we have n successes we have n successes in total. So this becomes n factorial. Essentially, we're just going to replace all of the x's with n's. Because x is n. If everything's a success, we succeed every single time. We had all the possible successes. Think of it this way. N minus n is 0. Anything to the power of 0 is 0. So this is gone. N minus n is 0. 0 factorial is 1. This is gone. N factorial over n factorial, that's 1. This is gone as well. So all we're left with is p to the power of n. That is the first shortcut. Our second shortcut, if we never succeed at all, we're saying it's going to be 1 minus p to the power of n. Why? Well, in this case, x would be 0. So that's going to be 0. And all these will be 0. Well, 0 factorial is 1. That's just going to go away because it's being multiplied by 1 over 1. n minus 0 is just n, so that's n factorial. N factorial over n factorial cancels out. Anything to the power of 0, well, it's 0, but it's not going to be 0, is going to be 1, so that goes away. N minus 0 is just n, so we're left with 1 minus p to the power of n. So these are the binomial shortcuts. So, in fact, if we always succeed to show us using the shortcut, that's going to be p, which is 1/2, to the power of 3, because 3 successes. Conversely, if we never succeed, that's this. So those are the binomial shortcuts. You'll find those to be very useful. Now let's come down here to 6. So with 6, we're asked, what's the mean? Well, if each question has 4 possible answers, and we're randomly guessing, then our p is equal to 1 out of 4, because 4 possible answers, so 0.25. So the mean is going to be equal to n, 10 questions, times the chances of succeeding, 0.25. So we'd expect with random guessing to get a 25%, which lines up with our heuristic. Now, what are the chances of getting exactly 6 correct? And here, we're going to use our binomial distribution again. So here, this is denoted by b of 6. So here is our binomial distribution. Let's start actually replacing values. So we have a total of n questions, which is 10. So we're going to replace all of these n's with 10. And our p is 0.25. So we're going to replace these with 0.25. If you wanted to, you could go straight into Desmos and literally write in b of x is equal to this and just type that in. If you do that, you could then say you could literally just type in b of 6 and it'll spit out the answer, which in this case would be 0.016. Again, that just comes from typing this straight up, word for word, letter for letter, number for number, into Desmos, and you just enter in b of 6 and it'll give you the answer. In fact, on the test, this is exactly how you should do it. But if you want to see the full work, we would have this. We would have 10 factorial divided by, in this case, x would be 6, so we'd have 6 factorial times 4 factorial times 0.25 to the power of 6 times 1 minus 0.25 to the power of 10 minus 6, so 4. You put that in your calculator and it'll spit out the same 0.016. So now I want to give you example number 7. The difficulty level of the binomial questions will be no more difficult than this. So here, I want you to find the mean number of leaky roofs, and then find the chances that at least 2 of the roofs will still leak. Here's what I'm going to do. I'm going to give you a moment, and then I'll go over the mean number of leaky roofs and then give you a hint for the remainder, because you might find the second part to be more difficult. So see if you can do both these now. If you're getting stuck on the second part of finding the number, the chances that at least 2 of these roofs will still leak, if you're getting stuck on that, I'll give you a hint in a moment. So here are the mean number of leaky roofs. In this case, how many roofs do we have? Well, we have 8 roofs, if we want to pronounce it that way. And the chances of it leaking is 15%. So, this, 8 times 0.15, on average, 1.2 roofs will leak. This is an example of where the mean can't be a data value, like with when rolling the die. Doesn't mean it's wrong, it's still right. It means most of the time, 1 of the roofs will leak, 1 or less at least, but every now and then you'll have more than 1. So now let me give you the hint. Here's the hint. We want b of x being greater than or equal to 2. Look at all the outcomes that composes. You would need to get b of 2, b of 3, b of 4, b of 5, b of 6, b of 7, and b of 8, and add the whole thing together. So you would literally, and this is where I'm just going to type it, that would be equal to b of 2 plus b of 3 plus b of 4 plus b of 5 plus b of 6 plus b of 7 plus b of 8. You can technically do that, but there's an easier way, the complement law. This is equal to 1 minus the chances of x being below 2. So now that you have this hint, if you got stuck, see if you can try to solve it now. All right, so let's now fully solve it out. Here we have our wonderful binomial back again. In this case, we have 8 roofs, so our n is going to be 8. So let's put that in for all of our n's. And our p is 0.15. And this is our b of x. If you enter this straight into Desmos, you're nearly there. Well, if x is less than 2, constructing our complement, the only 2 ways you can be less than 2 is if nothing leaks or only one thing leaks. So this is equal to 1 minus b of 0 plus b of 1. I put these in parentheses because this is equal to that. So if you enter this into Desmos, you can literally enter in this, and it will give you the correct answer. Regardless, b of 0 plus b of 1 is 0.658. So the chances of at least 2 of the roofs leaking is 34.2%. You would have gotten the same answer if you did this whole thing. And if you wanted to, if you have this entered into Desmos, I suppose you can type this whole thing out. That's a lot of work and a lot of time for something that can be solved much easier. Now, on the test, you're going to get a problem very similar to this difficulty level. Very, very similar. Here's what would happen. Or at least you might have it on your test if you have me as your instructor. What will happen is you'll have this 0.342 as a correct answer. 0.658 will also be a correct answer. You get partial credit because you misread the problem, but it wouldn't get full credit. Additionally, b of 0 would be an answer. B of 2 would probably be an answer as well. Because someone might say, oh, b of 2, I'm done. Well, no, you still have the parts below it. But with binomial, this is the extent of the difficulty level. And I'd note, this one is an example of how a success might sound a bit paradoxical, because this contractor, he's trying to fix the roof. You fix the roof and you fail, you might think that's a bit of a failure if you ask me. Well, in this case, defining a failure as a success makes the math a bit easier. So that was an example of why we put success in quotation marks and failure in quotation marks. So now, we're going to proceed to the ugliest distribution in the course. It's a complete train wreck, and it is the hypergeometric distribution. With binomial, we had replacement. For hypergeometric, we do not, and you get something that is so monstrous that I can't even fit it without zooming out. So let's start with the part that'll be easier to see. I recommend writing this down first. So the hypergeometric distribution is a complete circus. It is a clown car. It is a clown fiesta, and it induces sadness and despair onto all of those who see it. when you see the full formula, you'll need to go schedule an eye doctor appointment to get some corrective lenses because it will permanently damage your eyes forever. So x is still the number of successes. Now we have two n's. We have lowercase n, which is our sample size, and we have capital N, which is our population size. Sometimes these will be the same, sometimes they won't be. R is the number of population elements that are success. So we really have two pairs. These two are a pair, and these two are a pair. We have the two n's. Lowercase n is still sample size. Uppercase n is population size. R is the total number of things in the population that are successes, and x is the number of those we're looking to pick. In this case, our P is equal to R over N, because right off the bat, R of them are successes and N is a population size. So we use this when binomial does not apply. So binomial is for replacement, hypergeometric is for non-replacement. Before I show you the horrible, ugly formula, I want to explain what non-replacement means. Let's go back to the example of picking cards out of a deck. Let's suppose you're playing Texas Hold'em Poker. Texas Hold'em Poker, you get two starting cards. You cannot get the Ace of Hearts twice. There's only one Ace of Hearts. If I asked you what are the chances that your starting hand in Texas Hold'em Poker is two aces, you're not going to do 4 out of 52 times 4 out of 52. Because if your first card is an ace, that decreases the chances of the second one being an ace. Put another way, you're not replacing the ace back into the deck. So there's non-replacement. You know, you don't pick your card in Texas Hold'em and say, I don't like it. Put it back and give me another one. Unless you're playing a house roll, which then is no longer Texas Hold'em. It's Texas, throw them away. But Hold'em and throw them away, not the same thing. Regardless, binomial is for replacement. Hypergeometric is for non-replacement. So, let's now zoom out. Yeah, it's this whole thing is the hypergeometric formula. And it's denoted by h of x. It's ugly. It's horrible. And it induces sadness on anyone who looks at it. Thankfully, we have some shortcuts. Where are the shortcuts? Yeah, we have shortcuts down there. I'll show you the shortcuts in a moment. Here's the good news. Most of the time, when we're dealing with non-replacement, we care if it always succeeds or always fails. So the good news is that when it comes to hypergeometric, you usually get to use the shortcuts. That's not the case with binomial. Then again, with binomial, it's not quite as ugly. Now, if you are a sadist and you want to torture yourself with this thing, in the Desmos Assistance video, I show you how to deal with this whole tortuous, horrible thing. But, at least with me, Professor Bailey, for my tests, if you have hypergeometric, you would get to use shortcuts. So before I get to the shortcuts, it does not matter if you know how to do the computations if you cannot even figure out which one to use. So here, I have 4 practice ones, and all I want you to do here is figure out whether you would use the binomial distribution or the hypergeometric distribution for this one. So let's start with part A. You have a deck of 52 cards, and you're choosing all 4 at once. How many of you think that would be binomial? And how many do you think that would be hypergeometric? That would be hypergeometric distribution. Because, since we're choosing all 4 at once, there can't be replacement. You could theoretically pick all 4 aces. You got to run the table. You can't pick the same ace 4 times. Because it's all at once. Now, second one. We flip a coin 3 times, back to back to back. So you flip it once, then flip it again, flip it a 3rd time. Same coin every single time. How many of y'all think that'd be binomial? How many of y'all think that'd be hypergeometric? And that is binomial. We are literally replacing the coin. You might say, no, we're not. It's the same coin every single time. Think of it this way. If we took a penny and we switched it out for another penny, Same damn penny, still useless. Pennies aren't worth anything. Doesn't mean you can't flip it though. Doesn't matter if you flip one fair penny for another penny, still a fair penny. You're replacing it every single time. Now, part C, we're going to have a series of multiple choice questions, 4 answers each, and you're guessing on all of them. How many of y'all think that's going to be binomial? How many of y'all think that's going to be hypergeometric? This one's binomial as well. Although it's a different question, you get the, if you want to, that's not how you spell binomial at all. There we go. If you want to, you can replace every single time. You can put answer choice A every single time. Just because you picked answer choice A on the first question, that doesn't mean, oh, well, can't pick A now. So you literally have the replacement of the answer choice. Finally, part D, you're playing blackjack and you reveal the 3 river cards. And they're chosen one by one from the deck without putting them back in. You might say, this one's nonsense, I have no idea what blackjack is. Well, if you don't know what blackjack is, I can explain it anyways, then you'll see why you don't need to know what it is to get the correct answer. With blackjack, you get your 2 cards. In some variants of blackjack, they'll reveal cards off the top. This is the dealer's hand. The dealer has to follow a certain set of rules. And the dealer starts with 2 cards. He flips them over. Dealer keeps flipping until he hits 17, not a soft 17. So, the 3 are called the river. The first 3 flip are called the river. Same with Texas Hold'em, it's called the river. Can't have the same card twice, unless they're using multiple decks, but still technically not the same card. So, since we do not have replacement, this time it'll be hypergeometric. Can't have the Ace of Hearts 3 times in a row. Again, unless they have a deck of 3 decks composed, but then again, you still can't get the literal same Ace of Hearts cards multiple times. So now that you can differentiate between them, let's talk about the shortcuts. The shortcuts make us happy inside. They make life easier. And most of the time, it means we get to ignore this god-awful thing. So here I introduce you to the shortcuts. The binomial shortcuts, I already showed those to you. Now let's talk about the hypergeometric shortcuts. Again, we're dealing with the boundaries, always succeeding or always failing. In this case, remember this guy? The product notation is back. I introduced it before, but I'll talk about it again. Product notation is similar to summation, but instead we multiply all the things together. So here you might say, what in the Lord's name is going on here? What is even happening? What in the good Lord baby Jesus? Please explain. So here, like with the summation notation, if it helps you, you do that for every value of I. So N and R are fixed. They don't change. These N's don't change. They're given in the problem. So if you have a deck of 52 cards, then capital N will be 52. And if you're looking for the queens, lowercase n, there'd be 4 queens. If you're picking 4 cards. If we're picking 4 cards, 4 N's. And if you're looking for the queens, R would be 4 as well. So, for example, let's suppose we have a deck of 52 cards. We have 4 queens. And we choose 2 cards. Let's say it's Texas Hold'em. What are the chances of getting 2 queens? What are the chances of getting no queens? Let's think of it this way. So both queens. And then no queens. We have to use hypergeometric because we can't get the same queen twice, but we get to use the shortcuts. I'm going to show you how. In this case, it's easier to show an example instead of some arbitrary notation. Let's start with part A. So in this case, our capital N is 52. In both of these cases, we have a total of 4 queens in the deck. We'll recall that R is the number of successes a queen is succeeding. And our sample size is 2. So now let's start with part A. Let's just set up the formula itself. We have I equals 0. Lowercase n is equal to 2. So we have 2 minus 1. And on the inside, we have r minus I, so our r is 4. And then we have capital N minus I, so 52 minus I. So this is what it's going to look like. What does that mean? Well, first we start with I equals 0. So we have 4 minus I, so 0 in this case. And then we have 52 minus 0. So this is the chance of the first one being a queen. Now that we've got that, let's go to the next one. Now I is 1, and we're stopping at 1. So 1 is our last one that we're going to do. This time we have 4 minus 1. So like with the summation notation, we add them up in order. So we start from 0, next one is 1. Now we have 52 minus 1. So now that we've done it, we're multiplying them together. Because product notation, we multiply everything together. 4 minus 0 is 4. 52 minus 0 is 52. Now we have 4 minus 1, that's 3. 52 minus 1 is 51. To convert this to English, this is the chance of your first one being a queen, and this is the chance of your second one being a queen, given that the first one was a queen. So therefore, the total chances of getting a queen is going to be 4 times 3 divided by 52 divided by 51, so roughly 0.452%. Okay, let's do part B now. Part B, we're asking what are the chances you don't get a single queen in your hand? Playing Texas Hold'em. So here we start with I equals 0. And we go to lowercase n minus 1, so 2 minus 1. And now here, we have capital N, 52. Minus r, which is 4, because we have 4 queens, and then minus I. And we divide this by capital N minus I, so 52 minus I. So this is equal to the product of these things. 2 minus 1 is 1, and we start from 0. So we're going to do 0 and 1, and that's it. If 1 was instead 2, we would do 0, 1, and 2. So now we have 52 minus 4, 48 minus I then. And then we have 52 minus I. Now that we've done that, let's actually work it out. We start with I equals 0. So 48 minus 0 is 48. 52 minus 0 is just 52. But we'll include the minus zeros anyway, so you can see where it's coming from. So now we've done that. We're multiplying. We're on to the next one. So now we're going to increment I to 1, and 1 is our last one, so we're going to stop here. This is our last one. So now we have 48 minus 1. We're just replacing I with 1. And then 52 minus 1. So this will be equal to 48 out of 52 times 47 out of 51. In this case, 48 out of 52 are the chances of not getting any queens. And then 47 out of 51 are the chances of not getting a queen, assuming that we already hadn't gotten a queen. And we have to multiply them together. So therefore, 48 times 47 divided by 52 divided by 51. There's a roughly 85.068% chance that you won't get any queens in your starting hand. Notice how this is way easier than using this whole big nasty thing. I recommend you don't use this. You can if you want to. And in the decimal assistance video, I show you how to, but I'd recommend using the shortcuts. So now that you have these shortcuts, what I want you to do is use the shortcuts to do all parts of these. These are all real life examples. I know some of you like your video games, so we have a video game one. I know a lot of you like the card games, so we have a couple of those. And then, of course, we have a dice game. So, I'll give you a moment to work on these. Then I'll go over the answers. What I am going to do, though, is we'll first identify whether it's binomial or hypergeometric. And then I'll draw an arrow to which shortcut it is. So that way, if you incorrectly identify the distribution or incorrectly identify the shortcut, you'll have a second chance to at least do it correctly. So let's first identify the distributions and what shortcut will apply. And then I'll give you another moment if you mess those up, so you have another chance to do it. So we're picking 4 cards from the deck, all 4 as kings. We're picking all 4. And since we're doing all 4 of them, there's no replacement. So this is going to be hypergeometric. Now we want all of them to be kings. So always A. That's going to be this one. Number 2, we have this hill giant, and we're killing separate hill giants. These things respawn. Welcome to video games. Gotta make an infinite economy somehow. Otherwise, people won't be happy. Welcome to the world of instant gratification. And there's a 1% chance for Crimson Charm. So in this case, it's a Bernoulli trial. You get a charm or you don't. So that's going to be binomial because we have replacement. New hill giant every single time. So we're asking that we always get a Crimson Charm. So therefore, that's going to be binomial for always A. Now the third one, we're rolling a fair 6-sided die 4 times, and we never get a 1. So we re-roll it, do it 4 different times. We use the same die every single time. We're literally replacing the die. Therefore, this one will also be binomial because we're replacing it with itself. So, but we're never getting a 1. So this is going to be the never shortcut. And finally, the fourth one, we're back to our deck of cards. We're never getting a queen. And so here, there's no replacement. So this will also be hypergeometric, as with number 1. But this time, we're never getting a queen, so we use the never shortcut. So now that you know which distribution it is and which shortcut to use, if you messed it up, I'm going to give you another chance to work on it again so we can maximize the chances of you at least getting some understanding of what's going on here. So I'll give you a moment, and then we'll go over the answers. So, in this case, let's start with 2 and 3, because those are computationally a bit easier. So for 2, it's always A. This is equal to chances of A occurring to the power of n. Well, the chances of getting a Crimson Charm are 1 out of 100, because 1%. And we're doing it a total of 3 times, because 3 in a row. So that's the power of 3. And this comes out to be 10 to the negative 6. Our third one, we're asking for the chances of not getting a 1. Well, the chances of not getting a 1 are 1 minus 1/6 by the complement law. Chances of getting a 1 are 1 out of 6, so complement law 1 minus 1 out of 6. And we're rolling it a total of 4 times. This will be equal to 5 out of 6 to the power of 4. And if you wanted to put that in decimal form, that would be about 0.482. Now, let's do 1 and 4. I'm going to do these up here where we have more space. The first one, we're getting all 4 as kings. So we're going to set up our product notation. We always start with I equals 0. Here, this time we're picking 4 kings. So our sample size is 4. So 4 minus 1 is 3. Okay. Now, R minus I, in this case, we have 4 kings in the deck. So 4 minus I. And then, we have a total of 52 cards, so capital N is 52. This is minus I. So now let's do the product in order. So first, I equals 0. 4 minus 0 is just 4. 52 minus 0 is 52. All right, now our next one, we're going to increment I to 1. 4 minus 1 is 3. 52 minus 1 is 51. Now, since our stopping point is 3, we're going to go past 1. Now we're going to make I 2. So now we have 4 minus 2, which is 2. And then we have 52 minus 2, which is 50. And then finally, we have I equals 3. This is our last one. So we have 4 minus 3, which is 1. And then 52 minus 3 is 49. This whole thing is going to come out to be extraordinarily small. 3.694 times 10 to the power of negative 6. If you're drawing 4 cards, you ain't getting 4 kings unless the good Lord is smiling down upon you. All right, now let's do the other end of it. Let's say we're picking 4 cards and none of them are queens. This one is going to be our never formula. So let's set this one up. Again, we always start with I equals 0. We're picking 4 cards, so 4 minus 1 is 3. So we're going to go from 0 to 3. And now we have capital N, which is 52, minus R, 4 queens. So 52 minus 4 is 48. And then we have that minus I. And our denominator is just going to be capital N minus I. So 52 minus I. Now, let's go ahead and expand this out. Our first one, we start with I equals 0. 48 minus 0 is going to be 48. 52 minus 0 is 52. Next one, we're incrementing I to 1. Now we're doing I equals 1. 48 minus 1 is 47. 52 minus 1 is 51. Now we're going to go to I equals 2. 48 minus 2, 46. 50 minus 2, I'm sorry, 52 minus 2 is 50. And then finally, we have I equals 3. So 48 minus 3 is 45. And then 52 minus 3 is going to be 49. So this is going to come out to be roughly 0.719. So if you pick 4 cards, there's a 71.9% chance that you don't get a single queen. Those are the shortcuts. That's all we have for binomial and hypergeometric. So finally, let's go back to the normal distribution. We dealt with working backwards. Let's now get probabilities. So let's suppose that we have a normal distribution and we have 2 z-scores, ZV and ZW, and I want to know what the chances are of being in between 2 of these values. Since the normal distribution is continuous, because we're allowing all the z-scores, like with the uniform distribution, the chances of being between these 2 values can be expressed by either of these. So we're just going to stick with the less than and greater than symbols. And then in a similar vein, the chances of being less than or equal to some value is the same as being less than that value. And likewise, the chances of being greater than or equal to some value are going to be the same as being greater than that value. Again, because of continuity and the whole 1 over infinity thing. So we stick with this notation. You don't have to write this down. It's just notation. So now we have this normal distribution. What if I asked you, what are the chances of being in between these two values? You might say, I don't even know what are the chances of being below one of them. How am I supposed to figure out what's in between both? Well, think of it this way. This whole thing right here are the chances of being below ZV. So we're going to denote this as P of Z is less than ZV. Okay? This whole thing constitutes the chances of being below ZW. So we're going to call that P, Z is less than ZW. So if we subtract the overlap between the two, put another way, if we have this area and we knock this part out, then we're left with what we're looking for. So if we subtract this probability from this probability, then we get the area in between. So therefore, in this part you do need to write down, the chances of being in between two z-scores is equal to the chances of being below the lower one minus the chances of being below the upper one. You might say, what are ZV? What are ZW? You have not told me what these are. These are just letters. You'll be given the actual numbers momentarily. So now let's go to some real hard depictions. Here is an example of being in between two z-scores. This would be ZV, and this would be ZW. So in this case, ZV is negative 1/2, and ZW is positive 1 1/4. So the chances of being in between these two z-scores, the chances of our z-score being from negative 0.5 to positive 1.25 is equal to the probability of being below 1.25 minus the probability of being below negative 0.5. You might say, okay, fine. What does this mean? This is very useful for the normal distribution because the normal distribution pops up all the time. In fact, if the sample size becomes sufficiently large, the binomial distribution is approximated by the normal distribution. I'll go over this more with the central limit theorem in Unit 3, but for now, just accept that this is extraordinarily important. So let me give you a hard example of the computation. Let's suppose I asked you, what are the chances of being between negative 1 and positive 1? So within one standard deviation of the mean. You already know the answer, 68%. Let me now show you why that's the answer. So here, oh my lord. Here we go. So here, this is ZV, and that is ZW. So the probability of being below negative 1 is 0.1587, roughly 16%. The chances of being below this guy is 84.13. This is 84%. Again, we remember that from the empirical rule. So therefore, we subtract this guy from all of this to give us this. And so therefore, we have 0.8413 minus 0.1587 is equal to 0.6826. So the chances of being in between these two is roughly 68%. Oh, I'm sorry, I drew the arrow the wrong way. PZ is less than or equal to 1 is right there. This shows you where the empirical rule comes. There's a reason why with the empirical we rounded it to make it easier to understand. Now you might say, okay, fine, this makes sense. Where are these numbers coming from? I'll show you in a moment. I just want to give you a couple more examples. This one, the chances of being below 1, that comes from a table, so I'll show you in a moment. Now here I want to show you the complement law. The complement law, P of z is greater than zw, is equal to 1 minus P z is less than zw. That's the complement law. You need to write this down. So how do we do that? Easy. So in this example, I'm asking you, what are the chances of being above 1.58? Well, if we get the chances of being below 1.58 and subtract that from 1, that'll give us the chances of being above 1.58. You might say, okay, I get that, but again, what's the point? Well, here's why. If we have a table telling us the value of being below any given z-score, we can use the complement law to figure out the chances of being above it, and can therefore also use it to find the chances of being in between. A table. The z-tables. Let me now give you the z-tables. These are the z-tables. The z-tables tell you the probabilities of being, or the probability of being to the left, i.e. below, any given z-score. These z-tables are provided, again, if you have made Professor Bailey there in Blackboard, most instructors should have this in Blackboard in one way or another. For my sections, this is it's inside of the Learning Materials folder. You'll see a folder called Tables. Open up the Tables folder, and it's called Z-Tables. It'll show you these two images. For my sections, at least, you can print these out and have them by you for the test. And it does not count against the cheat sheet. Again, cheat sheets for my sections, not necessarily for others. But for mine, Professor Bailey, you get to have cheat sheets. So, you might say, oh my lord, this is a lot of numbers. Tell me how to read it. I need to learn how to read. Please help me read. Here's how. What you first do is look for your z-score. So let's suppose we have z is equal to 1.31. First, look for the 1.3. That's your first decimal place. Then look for the second decimal place. Our second decimal place is 0.01. Draw the arrows down. And therefore, the probability that z is less than 1.31 is equal to 0.9049. That's it. Nothing else to it. Now, let's suppose we have z is equal to negative 1.03. That's going to be on the lower tables. So let's look. We're looking for negative 1.03. So the first decimal place is 0. The second decimal place is 3. So therefore, the probability of our z-score being below negative 1.03 is equal to 0.1515. Indeed, if you look for just negative 1, the 0.1587, that's where that comes from. So therefore, if I asked you what are the chances of our z-score being in between these two z values, that is equal to this minus this. I'm sorry, other way around. So that would be 0.9049 minus 0.1515. So therefore, 0.9049 minus 0.1515, 0.7534. That's it. Nothing else to it. So I'm going to give you 3 practice ones. This is straight out of web work. You might have these numbers, you might not. So here what I want you to do, I want you to find these probabilities for the standard normal distribution and use the z-tables. Do it the exact same way I did there. Our first two are just in-betweens, and our third one is the complement law. So I'm going to give you a moment to use these. Go and work them out, and we'll go over the answers. All right. So our first one, this is equal to the probability of z being less than 2.45 minus the chances of z being less than 0. For our second one, this is equal to the chances of z being less than 0.8 minus the chances of z being less than negative 1.25. Our third one, complement law, this is equal to 1 minus the chances of z being less than negative 1.25. So if you messed one of those up, you can go ahead and try again to use the tables. But otherwise, let's go over these answers. Let's start with the third one. This is equal to 1 minus the chances of z being less than negative 1.25. So here, I'm now going to switch to colors so you can clearly see which is where. So, the negative 1.25, first look for negative 1.2, the first decimal place. Then we're looking for the 5, which is our second decimal place. Draw our arrows down. So we're going to have 1 minus 0.1056, which is equal to 0.8944. That's our probability. Let's now go back up. I'm going to use blue for this one. So, the chance of being below 2.45, first the 2.4, then the 0.5, so 2.45. So that is going to be 0.9929. The chance of being below 0, you can use the table or use common sense. Half the data is below 0, so it's going to be 0.5. But if you wanted to use a table, there's the 0.0, 0.00 right there. And therefore, our answer is going to be 0.4929. Let's do the last one. I'm going to use purple for this one. I'm using the color coding so you can easily see which ones are for where. First, we got to get the chance of being below 0.8. So, the 0.8 is right here. And we have 0, 0 again. So, the probability of being below 0.8 is 0.7881. And now, we need the chance of being below negative 1.25. Guess what? We've already done that. Merry Christmas. Happy New Year. Happy Hanukkah. Whatever. It's going to be 0.1056. So our answer is going to be 0.6225. That is the extent of complications for z-scores and finding probabilities in between them. As a final note, if you wanted to find the probability of not in between ZV and ZW, that would be equal to 1 minus the probability of being in between the two. Again, just complement law. So you'll remember when we worked backwards, we had that pair of z-scores with their x values from the previous lecture. The second part to that problem would be to find the probability of being between those two z-scores. So just imagine that. Just imagine how useful that is. All that we had, all the way back then, was 2 z-scores and 2 x values. That's it. We had nothing else. And just with those two alone, we can get the probability of being in between them, of being less than them, of being more than them, or being outside of them. And we can also get the mean and the standard deviation themselves. This is why the normal distribution is so extraordinarily useful. You need very little information to take it and just run away with it and get so much information out of it. So with that, that is all we have for the normal distribution. The last thing is just a mere application. This one's also from WebWork. So here we're going to combine it together. We calculated z-scores in the previous lecture. We now got probability associated with them here. Put them together. So here we've got some light bulbs that are advertised to last for 60 to 100 hours. They're normally distributed with a mean of 6450 hours and a standard deviation of 250 hours. So what's the chance that a bulb lasts longer than the advertised figure? This is a real life example. And while you're working on it, I want to give you a reason why this is very useful. A lot of, say, medications or electronics or foods will have expiration dates. But many of you have probably found you can use it a wee bit after the expiration date. With medications, you can often use them at least a month or two after it and still be fine. And with many foods, you can often use them a day or two after the expiration date and be fine. So many of you might have at some point asked yourself, oh, well, then why the hell didn't they make the date a little bit later? The reason why is because if they make the date the 50-50 mark, then there's a 50% chance it won't last that long, and you'll make some of your consumers very mad. Probability, the normal distribution, is why expiration dates are usually earlier than the time it will actually expire. So again, another example of how what you're being shown here is very much so extraordinarily useful. The blabbering aside, let's get to the answer. Step number 1, we got to get our z-score. Our z-score is equal to our data point, which is 6,200, minus the mean, 6,450, divided by the standard deviation of 250. Xi minus mean divided by standard deviation. So here, 6,200 minus 6,450 is going to be negative 250. Divide that by 250. That's negative 1. So now we're asked, what's the probability that we last longer than ZV? Or put another way, the chances of exceeding it. Here, we have to use the complement law. 1 minus P, Z is less than ZV. So let's now go to our tables. Here, I'm going to use brown. So we're looking for just negative 1. So, negative 1, 0, 0.1587, which comes out to be 0.8413. That's it. We just combined what we did in the previous lecture with what you've learned now. On the test, this would be an answer choice, and you'd only get half credit because you did correctly find the z-score and got a probability associated, but you didn't use the complement law at the end. So that's our correct answer. Now, something I want to point out, you might ask yourself, what in the Lord's name happens if my z-score goes out past 2 decimal places? What if, so I'll type it out, and we're going to make this in black. What if my z-score is more than 2 decimal places? What if it is negative 1.271? What do you do now? Well, here's what we do. I'll use this color. Let's suppose we had negative, I'm going to make that a little bit higher. Let's make this 1.571. Yep, make it easier. There we go. Negative 2.271. You might say, well, what do I do? You screwed me. It's not on the table. Because sure, there's negative 2.2. And now we have the 7. Where's the 1? What do I do? We're screwed. No, you're not. Round it. In this case, we would round and take this one. And we would say roughly, not exactly, roughly 0.0116. As a practical matter, it'll be a teensy-weensy bit lower than that. So you might say, okay, on the test, what's going to happen? At least for my sections, z-scores will be 2 decimal places for the tests. You might say, fine, what about WebWorks? On WebWork, there's increased tolerance. So, for example, the probability might actually be 0.0115. I have directed WebWork to give you a little bit of leeway. So even if you round it like I did here, it'll still get marked as correct. So round to your 2nd decimal place for the z-scores. Now, the probabilities, don't round those. Don't round till the end. But otherwise, that's all we've got for Unit 2. Hope you all have a great weekend. Stay safe, stay warm.